Okay, welcome everybody. Thanks for coming. We are the Language Model Meets CogSci Science Workshop. Obviously a lot of really cool stuff happening in the space. When we first thought of this workshop like a year ago, we're like, oh, it'll be really cool and like cutting edge. We didn't realize how like crazy things we're gonna get. So I think we're all just like really excited for what we're gonna hear today.
For sure. I mean, just for context, when we were originally submitting the proposal for this workshop, I think this is when GPT-3 was cutting edge, and all of the papers about GPT-3 were coming out.
Yeah.
And maybe a month after submission, GPT-4 came out, and everything changed, I guess. But hopefully our talks are up to date and cover some of the new stuff that's happening in the field.
We do have some amazing speakers. So all the speakers will have half an hour. All the speakers, I will have these 0 and 5 cards that I'll show you just with the number of minutes you have left. We will also email you the Zoom link to use to sign up. We're going to end with a 1-hour panel discussion with all our in-person speakers. And so if you have any like more general questions, hold up on those with like the questions for the talks and just save that to the end. Any questions? Cool. Yeah, so our first speaker is Taylor Webb, coming to us from UCLA.
Awesome. Thank you for the introduction. Hi, everybody. It's good to be here. So I want to start by considering one of the big questions that I imagine is on everyone's minds and that I think we're probably going to be talking a lot about in this workshop, which is the question of whether large language models are really doing something that we could call thinking or reasoning or understanding in a human sense, or whether it's all an illusion and they're just sort of mimicking human thought. And here you can fill in your favorite analogy, whether that be Eliza, the early chatbot that wowed audiences back in the 60s, or Clever Hans, the horse that was supposed to be able to do arithmetic, but was just responding to cues from its trainer. And I think, many of us have recently had experiences that sort of vacillate between these two extremes, sometimes having incredibly impressive interactions with these systems that seem to suggest they're genuinely intelligent, and other times just having very baffling interactions that suggest they don't understand anything at all. And so what I want to say first is I think really this question isn't precise enough. And I think as cognitive scientists, one of the things we can really contribute to helping understand these systems is to take this very general question and replace it with much more specific questions. And so I have essentially sort of two components in mind. The first is the question of which cognitive processes we're interested in. So human reasoning is, of course, comprised of all sorts of different reasoning processes, social reasoning, physical reasoning, mathematical reasoning, and so on. And I think there's really no reason a priori to think that all of these processes should necessarily cluster together, especially in artificial systems. And so I think first we need to be careful to specify which specific cognitive processes we're interested in. And then the second component is this issue of which specific research question we want to ask. And so the first sort of 0th order question you might ask is whether language models have similar capacities as human reasoners. This is arguably like the most important question from a pure engineering or AI perspective. But then I think there are a couple of other questions that are maybe more interesting from a cognitive science perspective. And so the first is the question of whether language models are using similar mechanisms or similar algorithms as human cognition. And here I think it's perfectly conceivable that we'll discover cases where we have a system that maybe has something approaching human-like capacities for one of these processes, but achieves those capacities using very different mechanisms or very different algorithms. And then the second question is the issue of whether language models developed those capacities in a human way. And so here too, I think it's conceivable we might find cases where the system has human-like capacities and maybe even uses a similar algorithm, but it arrived at that algorithm through a very different developmental route. So in other words, you might have sort of human-like algorithms in the mature system that developed in a very unhuman-like way. And so this is all just to say, I think it's important when studying these systems to try to be clear about the specific processes we're studying and the specific research questions we're asking about those processes. So in that spirit, what I want to talk about today is a specific kind of reasoning, namely analogical reasoning. And I'm going to be talking mainly about the question of capacities, but ultimately I'm interested in this question because I'm interested in the underlying mechanisms. So at the end, I'll try to offer some sort of informed speculation about the mechanisms that might support these capacities and how that might relate to human reasoning. Okay, so what's analogical reasoning? Analogical reasoning is essentially the process of comparing two situations and trying to identify how similar they are, but where this is typically distinguished from more basic similarity judgments by the level of abstraction that's involved in the comparison. So, usually when we're talking about analogy, we're talking about a comparison between two situations that are superficially quite different. So, for instance, if we're considering the analogy between large language models and clever Hans the horse, these are two very different kinds of things, AI systems of horses. But nevertheless, we can often identify more abstract correspondences between these situations, and that's what analogy is all about. So if we think about this classic distinction between crystallized intelligence and fluid intelligence, where crystallized intelligence means basically all the stuff you already know, and fluid intelligence means roughly your ability to figure out new stuff or solve new problems. There's actually, I think, good evidence that analogical reasoning is really central to our capacity for fluid intelligence. So if you take like all of the various tasks that are used to measure fluid intelligence and try to arrange them in a common space using multidimensional scaling, what you find is that analogy tasks actually seem to be some of the best measures of this general capacity in the sense that they capture the most sort of common variance amongst all these tests. And so there's a general sense that analogy is really at the heart of our ability to make sense of new situations. And it's a very important part of human thought. And I think it's something that we would want any like generally intelligent AI system to be capable of. Right, and so today I'm going to be talking mostly about a series of experiments that are described in a recent paper together with Keith Holyoke and Hongjing Liu, where we were interested in the question of whether large language models have a human-like capacity for analogy. And as I mentioned before, I think like many of you, I'm ultimately interested in understanding the actual mechanisms that support this kind of reasoning. But I think first, just like establishing whether they even have this capacity in any kind of general way is kind of a prerequisite to asking questions about the mechanisms. And so our goal here was just to try and determine across a range of different tasks how good these systems are at solving analogy problems. Okay, so the first set of tests I'm going to talk about are looking at matrix reasoning problems. So these are typically visual problems. This is a kind of visual analogy task where you have a 3x3 grid of geometric figures governed by some set of abstract rules. And the task is to infer those rules and use them to fill in the blank cell on the bottom right, typically by selecting from some set of answer choices. And so even though these problems are typically composed of very simple elements like circles, squares, and so on, they can actually be quite difficult, especially when you start combining multiple rules together. And in fact, the original version of these tasks, Raven's progressive matrices, is often considered like sort of the gold standard in terms of measures of fluid intelligence. And so this task seemed like a natural place to start, but this is of course a visual task, and so we can't just take these problems and like pass them directly to language models in terms of pixel level inputs. So instead, what we did is we created a text-based version of these problems that we call the digit matrices, where each of the cells in the matrix is demarcated by brackets. And instead of visual features like shape and size, we instead use digits. And so using this format, it's possible basically to recreate all of the major problem types that are found in the original Raven's matrices, but now in a text-based format that we can pass directly to GPT-3. And so the way we did that is we took these problems and just passed them to GPT-3 in this raw text format essentially sequentializing it using the brackets and line breaks. And then we had GPT-3 either directly generate a prediction for what would go in the final cell, or we also had a version that involved answer choices. But I'm going to focus on the generative case because I think that's a stronger test of understanding these problems. Right, and then most importantly, this evaluation was completely zero shot. So just going back again to this distinction between crystallized and fluid intelligence, analogy is really all about fluid intelligence of solving new problems. And so typically with problems like Raven's matrices, it's extremely important to test people without much practice. Otherwise, that sort of undermines the point of the task. And so throughout each of the tests I'm going to discuss, including the matrix reasoning task, but also others, it's important to emphasize that this is all zero-shot evaluation, similar to the way that human participants would approach these tasks. Okay, so these are the results for the digit matrices. So here we're comparing GPT-3, specifically the text da Vinci 3 variant, to a sample of undergrads. And basically what we found is that GPT-3 showed better overall performance on this task than human participants. So this figure is showing GPT-3 performance averaged across a number of different problems, and human performance both averaged across participants, but also with each dot representing individual participants. And so what we see is both GPT-3 and the human participants show a similar trend of decreasing accuracy with the number of rules in the problem, with the human participants having special difficulty on the logic problems, but overall with GPT-3 outperforming the human participants. Now, I should note that the best participant on this task actually got every problem correct. So the best human participant did actually outperform GPT-3. But the general trend was that GPT-3 was very good at solving these kinds of problems, and sort of better than the average undergrad. So we were very surprised by these results. We wanted to see to what extent they generalized to other analogy problems. So we essentially looked at all of the text-based analogy formats that we could come up with. And that included first these classic letter string analogy problems from Melanie Mitchell and Doug Hofstadter. And so the way this works is you have a transformation that's applied to a string of letters. So for instance, the string ABC might be transformed into the string ABD. And the task is to then apply that transformation to a target string. So for instance, if the target string is IJK, the correct answer would then be IJL. And importantly, we made sure to develop new letter string problems here rather than relying on those that are already on the internet. So those included relatively simple problems like this one, but also more complicated problems, and even problems like this one that involved sort of generalization from letters to real-world concepts. And so what we found is that these problems were actually more difficult than the matrix reasoning problems for both the human participants and language models. But here, GPT-3 still performed about as well, or maybe slightly better than human participants. Then next, we looked at this sort of standard 4-term verbal analogy format that's popular on standardized tests. There are 2 GPT-3 performed slightly better than human participants. And then finally, we looked at a set of story analogy problems where the task involved reading entire stories and deciding which amongst a pair of target stories was more analogous to a source story. And here we found GPT-3 actually didn't perform as well as human participants, but GPT-4 performed much better. And so overall, I would say we were really quite surprised to find that these kinds of models perform so well on these tasks, essentially as well or maybe even slightly better than an average sample of undergrads overall. And again, I just want to emphasize this is all zero shots, so no fine tuning, no in-context learning. And in the case of our matrix reasoning task, this is not only a novel problem set for these models, but is arguably a novel task, and so not the sort of thing that these systems would have seen before. And so I think taken together, I think these results provide a fairly compelling case for some sort of emergent analogical reasoning capacity in these systems. Okay, so I've been talking primarily about the capacities of these models, and in a second, I'll discuss some issues related to potential mechanisms that might underlie those capacities. But first, I want to say a bit about a notable failure mode that we observed in these models, because I think it helps to illustrate this point I want to make about the potential for dissociations between different cognitive capacities in artificial systems. So all of the tests that I've discussed so far essentially involve identifying analogies, maybe using those analogies to complete some pattern or select from a set of choices. But in human reasoning, people typically don't just make analogies for no reason. It's usually in the service of solving some problem or making an argument or something like that. And we did find the GPT-3 was able to do that in some contexts, but there was a particular task where GPT-3 just completely failed in a way that I think is really illuminating. And so this particular example comes from a developmental study where children were given a physical problem-solving task. And that task, the children are seated at a table with a bowl of gumballs in front of them. And the task is to transfer those gumballs to another bowl that's out of reach across the table. And and to do this, they're provided with a set of tools like a cardboard tube, a cane, and so on. But before trying to solve this problem, the children are first presented with a story about a magical genie who lives in a bottle and has recently moved to a fancier, newer bottle and wants to transfer his jewels from the old bottle to the new bottle. And the basic finding is that the solutions that children tend to discover were most often based on an analogy with specific variants of the story. So for instance, in one version of the story, the genie uses a magic staff to pull the new bottle over to the old bottle and then transfer the jewels by hand. And when children were presented with this story, they tended to discover solutions that involved using the cane to pull the bowl over to the bowl with the gumballs and then transfer them by hand. Whereas after hearing another version of the story in which the genie rolled up his magic carpet and then rolled the diamonds through it, in that case, the children tended to identify a solution that involved rolling up the poster board and rolling the gumballs through that, which is kind of interesting because they have a cardboard tube already, so they could have just used that, but they're very influenced by this analogy with the story. So we wanted to test whether GPT-3 could do something similar. So we described the problem setup and we presented these stories. And what we found is that GPT-3 was generally able to identify reasonable analogies in the sense that it could usually tell you which objects in the task corresponded to which objects in the story. But when you ask it to use that analogy to solve the problem, or indeed if you ask it to solve the problem in any way at all, it proposes completely nonsensical solutions. And so I'll just walk through this because I find it really entertaining. What it proposed in this case is to cut the poster board into a long strip, tape that strip to the end of a cardboard tube, tie the cane to the tube using the string, place the tube in the bowl of gumballs, somehow use that to try to pull the gumballs towards you, use the paper clip to secure the tube to the table, use the rubber band to secure the tube to the cane, which keep in mind is already secured to the cane with a string. And then somehow, magically this is supposed to result in the gumballs being transferred to the other bowl. And so obviously, this makes absolutely no sense. And I think this is consistent with what many other people have observed when trying to get these systems to do more sort of physical reasoning. But I think it's interesting because I think it sort of illustrates that despite being able to identify the analogy here without having some more basic understanding of the physical world, GPT-3 can actually use that analogy to generate a solution to the task. And so I think this is an interesting example of the kinds of dissociations between different cognitive processes that we might see in artificial systems that seem very strange from the perspective of human cognition. Okay, so in the remaining time I have, I want to just offer a few mostly speculative thoughts about the kinds of computations or algorithms that might be supporting this capacity for analogical reasoning. First, though, I have here an illustration of a traditional cognitive model of analogy. So this is the structure mapping engine of Daedric Gentner and Ken Forbes. And this model has a few features that I think are typical of cognitive models of analogy. The first is the model operates over structured representations that explicitly represent entities and sort of keep track of their relations with each other. And second, the model is like fundamentally organized around a mapping process where the goal is to figure out which entities in one situation map to which entities in the other. And so, throughout virtually all cognitive models of analogy, not just the structure mapping engine, but other models, this mapping process is typically driven by similarity. So the goal is to map either similar entities to each other or to map entities that have similar relations. And so this sort of model probably seems like quite far away from the world of large language models. But I just want to note that there are other more recent versions of these kinds of cognitive models where rather than symbolic representations, instead you have attributed graphs where the entities and relations are represented by vectors. And that then allows a mapping process that's sort of more distributed and is based on more graded measures of similarity, like cosine similarity. And I think when you look at analogical mapping in this way, it actually doesn't seem very far off from the way that transformers work, in the sense that the self-attention operation at the heart of the transformer architecture is primarily based on a kind of all-to-all similarity computation, where you have this dot product between queries and keys that determines how information is exchanged between different inputs. And so, I don't have like a fully worked out algorithm, but I think it's an interesting possibility that having similarity like baked into the architecture is a useful inductive bias that maybe encourages these models to do some sort of analogical mapping. But I just want to note, finally, even if it does turn out that language models are solving analogy problems using some sort of genuine analogical mapping process, that doesn't mean that they necessarily developed that mechanism in a human-like way. And in fact, I think they really aren't plausible models of the developmental process. They receive orders of magnitude more training data than humans do over the course of an entire lifetime. In this paper from Tom Griffiths, I think there was an estimate that this would be equivalent to continuously receiving language input like since the time of the ancient Egyptians. So way more training data than humans get. I think it's often suggested that maybe this can be viewed as analogous to optimization over an evolutionary timescale. I think that also doesn't really work. I think these really aren't plausible models of human evolution. Their entire training regime is based on sort of being optimized to match human language, which is sort of presupposed before the entire process, which poses a kind of like chicken and egg problem. But so I think, nevertheless, I think it's an interesting question whether, despite these very significant differences in developmental processes, human evolution and human development on the one hand versus like neural networks being optimized over all the text on the internet on the other, I think it's an interesting question whether these very different processes might have somehow converged to similar mechanisms, or whether they're maybe really solving these problems using fundamentally different kinds of cognitive mechanisms. And I think really either of these conclusions would be interesting. I think at the moment, it's basically an open question. I think in order to really satisfactorily answer this question, we're going to have to dig into the internal operations of these models, do sort of neuroscience experiments, neuroscience style experiments on them. And that also, of course, is going to require open source models where we even are able to access the internal states and try to figure out what's going on. Okay, so I think I'll leave it there. Thanks very much for your attention. Thanks to my collaborators, Keith and Hongjing. And if you're interested, please check out our paper. It'll be out in print soon, but it's on archive now. So thank you.
We have time for a few questions if people can ask. I think the first question is over here. Yeah.
And the first, thanks a lot. It was very interesting. In the tasking, which the model it was not working, so that the GPT that you try with before.
I did try with GPT-4, and if you really hold its hand and like tell it, like, you don't have to use all of these materials and please make the simplest proposal you possibly can, it sometimes proposed explanations that made sense. But for some reason, it really seems to want to propose these very elaborate, like Rube Goldberg machines where it connects everything together. And I have no idea what in its training data is causing that. But yeah, it doesn't seem to me out of the question that maybe this will be resolved in future models. But at the moment, even with GPT-4, it's very unreliable. I think.
Like piggybacking on that question, do you think it can ever solve this without grounding? Like it doesn't have any knowledge of physical objects and compared to multimodal.
I don't know. I don't want to make any strong predictions. I think in principle, it seems to me conceivable that it could solve this kind of problem without grounding. I mean, it receives information about the physical world through text, which is like a very low bandwidth channel through which to receive information about the world. I think probably it will be much easier in a multimodal embodied agent, I would say.
Question so when we're doing experiments between human and ChatGPT-3 about like the zero shot problems, so what is the gold standard or what is the label for the, so are they labeled as humans or would it just be by abstractable? So I was thinking if they were labeled as humans, would there be like some human bias inside the data generation process? So then we probably a better ChatGPT is not necessarily perform better or worse than humans. It's just that it is more easily to learn some adapters than others.
Yeah, so no, that makes sense. I think with a lot of analogical reasoning, it's often the case that if you're creative, you can identify multiple analogies. So there's not like one correct analogy. We tried really hard to set up these problems in a specific way so that there really was one clear answer. I mean, this is challenging, but like, you know, with Raven's matrices problems, for instance, this is the goal of the kinds of problems. So there will be a single clear answer. But I should note, there are cases where there were like common sorts of errors that I didn't go into here. And so you might think those are maybe like partially justifiable by some other rule. And there were many cases where GPT-3 identified those same kinds of errors very often. So there was also a correspondence between the kind of errors that GPT-3 and humans made, which you might see as a kind of like picking up on a partially justifiable alternative explanation.
Can take one more question?
Any like robust systems that call robust the model for like online.